In this video, we'll solve another polynomial inequality using test points. We want to solve the inequality 2x cubed minus 2x is greater than or equal to 3x squared minus 3. To solve using test points, recall that means that we need to find the boundary numbers, which are solutions of the associated equation. These boundary numbers then divide the number line up into regions where we can test a number to determine where solutions of the inequality lie. We want to first set this inequality equal to 0. We get 2x cubed minus 2x minus 3x squared plus 3 is greater than or equal to 0. Now we can set this equal to 0 to get the associated equation. And because there are 4 terms of the polynomial, we will factor by grouping. If we factor by grouping, the first 2 terms have a common factor of 2x, which leaves us x squared minus 1. The last 2 terms of negative 3x squared and 3 have a common factor of negative 3. When we divide by negative 3, we get x squared minus 1 is equal to 0. So now we see the common binomial of x squared minus 1 that we can factor out to get 2x minus 3 as the other factor. Now we can set each factor equal to 0 and solve. X squared minus 1 equals 0 gives us that x squared is equal to 1, and by the square root property, x is equal to plus or minus the square root of 1, or plus or minus 1. Then we also have that 2x minus 3 is equal to 0, or 2x equals 3, and x is equal to 3 halves, or 1.5. Now that we have our boundary numbers, I will place these on the number line. We have negative 1, 1, and 1.5. So the regions that we need to test are regions to the left of negative 1, between negative 1 and 1, between 1 and 1.5, and then to the right of 1.5. Those intervals then are negative infinity to negative 1, negative 1 to 1, 1 to 1.5, and 1.5 to infinity. A test point in each of these regions would be negative 2 lies in the interval to the left of negative 1. Between negative 1 and 1, we can use 0 as a test value. Between 1 and 1.5, there's no whole number or integer, so we would need to use a decimal value, so like 1.2. And then to the right of 1.5, we can use 2. With these test points, now we plug into the original inequality to see if we get a true or false statement. So plugging in negative 2, we would have 2 times negative 2 cubed minus 2 times negative 2. Is that greater than or equal to 3 times negative 2 squared minus 3? When we simplify that expression on the left, we would get 2 times negative 8 plus 4, so that's really negative 16 plus 4, which is negative 12. Is that greater than or equal to 3 times 4, or 12, minus 3, which is 9? And that is a false statement, since negative 12 is not greater than or equal to 9. Our second test point is 0, which is easier to work with. We would plug in 0 in place of x to get 2 times 0 cubed minus 2 times 0. Is that greater than or equal to 3 times 0 squared minus 3? On the left, we just get 0 is greater than or equal to negative 3. And that is a true statement. In the third interval, we plug in 1.2, so we have 2 times 1.2 cubed minus 2 times 1.2. is that greater than or equal to 3 times 1.2 squared minus 3? So you have to get your calculator out to help with this. We would get 1.056 on the left. Is that greater than or equal to 1.32? And that is a false statement. Lastly, we substitute 2 for x to get 2 times 2 cubed minus 2 times 2. Is that greater than or equal to 3 times 2 squared minus 3? So on the left, we get 2 times 8, or 16, minus 4, which is 12, is greater than or equal to 3 times 4 is 12 minus 3, which is 9. And that is a true statement. So this tells us then that the intervals where solutions are located are intervals B and D. So on the number line, we shade the intervals that correspond to those regions. So we shade between -1 and 1, and then to the right of 1.5. And then we need to determine what happens on the endpoints. So because this is greater than or equal to, we are permitted to include then the solutions that arise from the associated equation. So the endpoints or boundary numbers are part of the solution set. So we're going to put a bracket on those endpoints. So in interval notation, the solution of this inequality is bracket -1 to 1, close bracket, union 1.5 or 3/2 to infinity, close parentheses.